Hello everyone. So today we are going to start our chemical bonding class. This is our chemical bonding lecture number 3, but in overall it's our class lecture number 11. Okay. So this is O-level chemistry from Science Academy. The chapter that we are going to study today is the class lecture 11 of chemical bonding. Okay. So let's get started. Okay. So um, before I start, I I want to say that if you want the copy of this lecture sheet, please comment your mail ID in the comment section below, and I will send you the this class lecture sheet. All right. Okay. So let's start about metallic bonding. Okay. So what is metallic bonding? Look. So metallic bonding, as the name says, okay, just wait. As the name suggests, the thing is that metallic bonding occurs in metals only. Okay, so this occurs in metals only. How does this occur in metal, or why does this occur in metal? Look, the outermost shell of electrons the outermost shell of electrons of the metals are loosely bound. Okay, so that's what it says, isn't it? The outermost shell of electrons of metals are loosely held by the atom. As a result, the outermost shell electrons are easily lost to become free. Okay, now let's see. Let's look at a fresh window. Okay, for example, this is an atom, a metal atom with this outer shell electron. Okay, so we are only drawing the outermost shell. This is an electron, and the electron has got a negative charge. Okay, now what happens is that if if this atom now loses its electron, look, this electron is now lost. Okay, this electron has got out from the atom, so this electron is lost. So what we are left is we are left with a positive metal ion and the electron, which has now become free, because initially it was held by the attraction of the nucleus, isn't it? It was held by the attraction of the nucleus, but right now this electron is free. Okay, so that's the structure of the that's what I'm trying to say, that the outermost shell electrons in this paragraph, look, the outermost shell electrons of metals are loosely held by the atom. As a result, the outermost electrons are easily lost and become free to move. Okay, since the metal atoms lose their outermost shell electrons, the atoms now become positive ions, the cations. Okay, and so what in overall what we get is a structure like this. Okay, look at this structure. So um, these are the metal ions and these are the electrons. These are all the electrons. Okay, so these electrons are the outermost shell electrons that are lost by these metal ions. Okay, so what happens is that, look, this is an electron which has a negative charge. So this negative charge electron, and this is a positive charge metal ion, so there will be a positive negative attraction, which we call the electrostatic force of attraction. All right, so this electron would attract both this ion, this ion, that ion, and then this ion. Similarly, all these are the cases. All the electrons that are present everywhere, they continue attracting the metal ions. Okay, so these attractive forces that we are drawing, these all these attractive forces that we are drawing, all these attractive forces are called, what we are calling it as the metallic bond, and this is also an electrostatic force of attraction. But although this is strong, but this is not that much strong as they are in ionic bond. This is because the electrons here, the electrons are free to move. All right, okay, so the overall structure of a metal ion is, we have what here is like regularly arranged positive metal ions in layers surrounded by delocalized electrons. Many delocalized electrons. It's like floating. I mean, it's like, for example, if you are a positive metal ion, and you are just diving below the sea, then you are surrounded by water, isn't it? And you are the metal ion surrounded by water, sea of water. So similarly, it is imagined in this way, that metal ions are arranged regularly or placed regularly, surrounded by sea of delocalized or free electrons. Okay, so that is the structure of the metal. Okay, so now the fact is that when you are applying a force, when you are applying a force on the structure of the metal, what happens is that, look, this layer would slide. Okay, this layer would get enforced and would slide, but in as we have seen in case of ionic bond, that the layers, after just small amount of sliding, the layers has got disrupted, because same charges came beside each other. Okay, same charges came beside each other, so due to repulsion, the layers disrupted, the structure disrupted. But in this case, look, here are all the delocalized electrons. Okay, so even if this layer of metal slides, then they would still be held in place by the electrostatic attraction of these electrons. Okay, confused? Let's go into diagram. Now look at this diagram, that a force is applied, a force is being applied on the layer of the metal, and here look, the layer of the metal has slightly moved onto one side, but still they are held in place, due to the electrostatic attraction of the metal ion, of the electrons. Okay, so that means the layers of metal ions can easily slide over each other without disrupting the structure. That's why we say that when force is applied, the shape of the metal can be changed. That's why we are calling metals as malleable and ductile. Okay, now what do you mean by malleable? Malleable, you can remember it in this way, যে like in Bangla you can remember it in this way, যে পিটায় তক্তা বানাই দিব. That means it can be hammered into various shapes. That's what the meaning of malleable is. And ductile means you can say like that, কান টেনে লম্বা করে দিব, okay, in Bangla. And the actual fact is that when a metal is pulled or force is applied, tension force is applied, it can be drawn into wires, or it can be converted to very thin wires. Okay, now let's go to the structure of graphite. Wait, what? Oh, here all atoms are given as phosphorus. Okay, let me make one correction at first. These atoms are not phosphorus. These all atoms has to be carbon atoms. Okay, these are not phosphorus. This is just a typing mistake, maybe, I'm not sure. Okay, so what is the structure of graphite? Look, before starting the structure of graphite, we need to go into the structure of the outermost shell of carbon. Okay, so look, if this is a carbon atom, then in the outermost shell of carbon atom there are 4 electrons. Okay, how many electrons are there? There are 4 electrons. All are single. That means this carbon atom can form 4 single bonds. Okay, now what happens, just for instance, keep this in mind, that in graphite, I am sorry for the interruption. In graphite, I'm just writing graph. In graphite we have 3 of the single electrons forming covalent bonds with other atoms, and 1 electron doesn't form a covalent bond with any atom. So this electron does what? This electron gets out of the atom and becomes a free electron. Okay, this what happens in graphite. But what happens in diamond is what happens in diamond is, in diamond all electrons form covalent bond with other atoms. That means none of the electrons are free. Okay, all electrons have formed bonds. Okay, now let's go back. Okay, so look, let me show you over here. So this atom has formed bonds with 3 other atoms. Okay, so 1 electron here, in this case 1 electron will remain free. So on each and every atom 1 electron would be free, which tends to move, and thus they would conduct electricity. Okay, like this. So on each and every atom there is a non-bonded electron which becomes free, so that it can conduct electricity. Okay, so this is a single layer of graphite. Okay, now then what is the overall structure of the graphite? Overall structure of the graphite is like this, that this single layer, okay, no, this is a single layer like this here. So many single layers are placed beside each other like this, okay, in graphite. And what happens is that very weak, should I zoom it, very weak intermolecular force, a very weak attractive force, which we call the Van der Waals force, that also operates between the simple molecular structures. Very weak intermolecular force, the Van der Waals force, is present between the layers of graphite atoms. Okay, just look at the dots. These dots are representing the weak Van der Waals forces. All right, okay, and these forces are very weak and they can be overcome very easily, so that when you apply a force on one of the layer, now yes, if you apply force on one of the layer, the layers can move past each other very easily. I mean, this layer can move over this layer very easily, because only weak van der Waals force operates between the layers, which can be overcome very easily, for which graphites are slippery and they can be used as lubricants. Okay, but the graphite has got very high melting point. This is because this is because the covalent bonds present here, okay, the covalent bonds present here, the covalent bonds, these covalent bonds are really very strong. These covalent bonds are really very much strong. So you need to apply a lot of heat energy to break these covalent bonds, for which graphite has got a very high melting point. Okay, so here is a layered presentation of graphite. Okay, look at the hexagonal pattern over here. This is a hexagonal pattern, isn't it? The hexagonal pattern is present all through the layer. Here we also have the hexagonal pattern present, right? Okay, now let's go to the structure of diamond. Okay, so what happens in diamond? Just remember that few moments ago I have said that in diamond each carbon atom forms forms 4 bonds. Okay, so each carbon atom forms bond with 4 other carbon atoms, and carbon atoms has got 4 electrons in their outermost shell. Carbon atoms has got 4 electrons in their outermost shell. I'm sorry for that. Carbon atoms has got 4 electrons in their outermost shell, for which in diamond carbon atoms can form 4 bonds. All right, so no electrons are left for free movement, because all electrons are involved in bonding. So that's why diamond is not a conductor of electricity. Okay, look at the structure over here. Look, a single carbon atom is bonded to 1, 2, 3, 4, 4 other carbon atoms. Now this carbon atom will also be bonded to 4 other carbon atoms, but it is not shown over here because all bonds are not possible to be shown. Okay, but just don't get confused that these carbon atoms are showing single bonds. No, not like that. They would also form 3 other bonds. That means in total 4 bonds they would form. Okay, like this. Okay, so this, when an atom is forming 4 covalent bonds like this, then the arrangement around it is what we call the tetrahedral style. Now what do you mean by tetrahedral? Okay, so here tetra means 4, sorry, tetra means 4 and hedral means faces. Okay, so 4 face style. Now let me explain you the meaning of 4 faces. Just look at this structure, isn't it? Okay, look at this structure. Look, this atom is forming bond in 4 direction. Now you can imagine 4 different atoms here. Okay, all right, so this atom, so this single atom is forming bonds in 4 directions with 4 other atoms. Now this structure, this whole structure has got how many faces? Just try to count. Okay, let me tell you. So this is one face, isn't it? So this is number face 1, and this is one face. All right, this is one face. This is face number 2, and this is one face. This is face number 3. Okay, and now, okay, so we have drawn till now we have drawn 4 faces. Okay, let me draw it again. So this is face number 1. Okay, and this is face number 2. Okay, this is face number 3. Okay, and that is face number 4. So we have got 4 faces. If you're still confused about how to count the faces or how we are identifying the faces, let me tell you. This is A, this is B, this is C, this is D. Okay, so you can say that one of the face is A, C, D is a face. Okay, is a surface. Then A, B, C is a surface. Then A, okay, this is point A. So A, B, E is a surface, and A, E, D is a surface. Okay, okay, so these are the 4 surfaces that I'm getting. Okay, you might argue that B, C, E, D is also a surface, B, C, E, D, but actually it's not, because actually B, C and D, they are they appear here in this case as if they form a surface, but actually no, they do not form a surface. Okay, they do not form a surface. So we have got 4 surfaces or 4 faces for which, when a single atom forms bond with 4 other atoms, we call it a tetrahedral structure. All right, okay, so in diamond, one single carbon atom forms bond with 4 other carbon atoms, forming a tetrahedral structure. and you can imagine it as if let me go to the structure of graphite. You can imagine it in this way, as if the layers of the carbon atoms in the layers of graphite are now they are interconnected. Okay, you can imagine it in this manner. Okay, so here now each carbon atom, look, for example, this carbon atom, it is forming 1 2. Okay, I got caught over here, sorry. So for example, I'm talking about this carbon atom. Okay, this carbon atom. Okay, and for example this carbon atom. Okay, so now look, this carbon atom forms 1 2 3 4 4 bonds, isn't it? This carbon atom forms 1 2 3 4 4 bonds, isn't it? So, all right, so diamond can also be imagined in this way, that the layers of graphite are now interconnected by covalent bond between the carbon atoms. Okay, you can also imagine diamond in this way. So what happens is that, just now imagine, sorry, just imagine that the layers are now connected by covalent bonds. So as initially we have said that the graphite can, in graphite the layers can slide over each other because there is only a very weak attractive force between the layers, which we are calling it as the Van der Waals force. Okay, but here the layers are directly interconnected by strong covalent bonds. So can the layers slide over each other? No, the layers cannot slide over each other. That means, although graphite is slippery, but diamond is not slippery. Instead, diamond is very hard, but it has also got very high melting point because again, just like graphite, the covalent bonds are very strong. Okay, so that needs a lot of energy to break the covalent bonds, for which diamond also have a very high melting point. Okay, so diamond is hard, diamond is not slippery, so diamond is not a conductor of electricity, and diamond has got a very high melting point. Okay, these are all the properties of diamond. Okay, so now look, now what is graphene? This is, okay, so this is a graphene which has a similar structure like that of a graphite. Okay, let me zoom it. Look, this graphene also has got a sorry, it has also got those hexagonal structures just like graphite. So where is the difference between graphite and graphene? Look, graphite, where is it? Okay, graphite has many layers, but a single layer, just a single layer of graphite, we call it as a graphene. So this is a graphene, this is a graphene, this is a graphene. So a graphite, just writing phyte, graphite can be imagined as the combination of many layers of graphene. Okay, so graphite can be graphene can be thought as graphite can be thought as many layers of graphene. Okay, so this is the graphene, this is the graphite, and this is what we call a nanotube. Look at the structure of nanotube. Look, it has also got those sort of hexagonal structures, right? Okay, so a graphite can be imagined in this way, that for example, this is a single sheet of paper which is the graphene, and nanotube is like this. For if the layer, as if the layer of the graphene is unfolded like this. Okay, so this can be thought as the nanotube, and if you unfold it, then this is the graphene. Okay. Okay, so graphite, graphene, we have got all the ideas. So in terms of electricity conduction, graphene and the nanotube, the graphene, in all these structures we have 3 carbon atoms. We have 1 carbon atom forming 3 covalent bonds with other carbon atoms, or 3 other carbon atoms, and 1 electron remaining free, which means that the graphene, the nanotube, and this structure around here, which is also called the buckyball, they also are buckyball is, although very poor, but still the graphene, the nanotube, they all are good conductors of electricity. Okay, because in all of these structures 1 electron will remain free. But unlike graphite, graphene and the nanotubes, they are very hard because there are no layers, and if you want to deform this structure, then you have to put a force within a single layer. All right, within a single layer. It's like okay, let me show you. Okay, so graphite is like this. That means, look, I have here 2 sheets of papers. Okay, all right. So these 2 sheets of papers, they can easily, these 2 sheets of papers, they can easily move over each other when I am sliding. This is the case of graphite. Okay, so they can easily move over each other. So this is the graphite. But in case of graphene, this is a single layer, and you have to put force on this. See, look, I am trying to pull it. We have to put a force on this single layer, and it's very difficult to deform a single layer rather than sliding 2 or more layers over each other. Okay. So in graphene, we have to deform the single layer by putting force, which is very much difficult. And in nanotube, the case is the same in the nanotube. Okay. Okay. It's difficult to prepare a nanotube, but still I'm trying. Here you go. So this is a nanotube. So when you are trying to put a force on this nanotube, sorry, it's so much disturbing. Okay. So when you are trying to put a force on this nanotube, look, it's so much difficult to deform because this nanotube is also a single layer of graphite just turned into a cylinder shape, and it's very much difficult to deform, very difficult to deform. Just imagine it that holding the 2 ends of this paper and then trying to pull it apart. Okay. So that's the structure of graphite, graphene, nanotubes, etc. And all these things we are calling it as the allotropes of carbon. Okay. Now we are calling them as the allotropes of carbon. Allotropes. Now, what do you mean by the term allotropes? Okay. This is what we now need to know. Okay. So allotropes actually means that they are made up of same atom, so same element, but they have different structural forms. Okay, they have different structural forms. Like, look, the graphene, the graphite, the carbon nanotube, and then what we are calling it as the diamond. Okay, then diamond, graphene, graphite, nanotubes, they are all made up of carbon, but they are taking different structural arrangements, isn't it? They are taking different structural arrangements, but all of them are made up of carbon. So these structures, so these types of substances whose structures are quite different, or structural arrangements are different, but they are all made up of same type of atom, we call them the allotropes. Like look, in carbon we have got a tetrahedral structure in which one carbon atom is bonded to 4 other carbon atoms, but in graphite, in graphene, in nanotubes we have got one carbon atom bonded to 3 other carbon atoms. Okay, but all atoms are carbon, but they are just taking different structural formats. So these substances we call them as the what we call them? We call them the allotropes. Okay. Okay, so that's all for today, guys. Just keep in mind also the structure of silicon dioxide. This is also very much important. Okay, guys, that's the end of our chemical bonding chapter. Thanks a lot for your cooperation, and if you have any problem, please mention it in the comment section. And those of you who wish to take the class lecture, what do you mean by wish to take? You have to take the class lecture, those who are the students of Science Academy. So you in the comment section give me your mail ID, I will send you this class lecture sheet. Okay, and in the next class we will be starting electrolysis. Get prepared for that, the boys and girls. Till then, thank you.